Well, let me welcome you all to this Turing Lecture tonight. Particularly welcome to you in such large numbers, braving the coronavirus and wondering about whether we should all be gathering together. But this is an important occasion, actually, and delighted to see so many of you here. For those of you who don't know me, I'm Alan Wilson. I'm a Programme Director at the Alan Turing Institute. And it's very much my pleasure to chair this. And I've promised Mihaela I'll try and have a few words to say at the end by way of winding up. So I will look forward to that. The title is on the screen. In introducing Mihaela, she's as again, it's on the screen. No, it was on the screen, it's disappeared. I've got a different title slide, I think, to come. She has this wonderful title. She's the John Humphrey Plummer Professor of Machine Learning, AI and Medicine at Cambridge. So a multitude of skills implied there. And I think the title actually shows the range of her work, which will be evident tonight. She's also a Turing Fellow. She's very important to the Institute. She's a key player in our health strategy. And I think this is actually her third Turing Lecture. She's been awarded lots of prizes, most recently the Owen Prize for Preventive Medicine in Cambridge. She's a leader in machine learning-driven medical diagnosis and prognosis, handling the problems and challenges of comorbidities, the foundations of what will be in many ways the future of medicine. And you'll be aware, I think, between you in this kind of audience of the work that Mihaela's done in this field. But more recently, she's turned her attention and her skills to the challenge of explaining explainability, to the challenge of explainability, turning black boxes into white boxes. And this is the force of what she's going to be talking about tonight. So really pleased to welcome her, welcome all of you. And I'll hand over to Mihaela to give her lecture. Thank you, Mihaela.
Thank you very much, Alan, for the kind introduction, and thank you all for being here. My biggest worry while preparing for this talk on machine learning, interpretability, explainability, and transparency was that the talk itself may not be interpretable, explainable, and transparent. So what I decided to do is every time I believe the slide itself may be somewhat of a black box unless you know about machine learning, I put a red dot over there. However, there are not too many red dots, so hopefully this will be sufficiently interpretable. I got interested in this area of explainability and interpretability of machine learning methods around 1.5 years ago, when together with Public Health England, with Dr. Jem Rashbas, we started to develop a decision support system for cancer patients, which was AI-enabled. I'm not going to tell you about that work in detail. If you are interested about it, it is a talk that is a Turing talk that you can find online. What I'm going to do, though, today, just very briefly, I'm going to take you to how I got started to be interested in interpretability and explainability of machine learning while I was doing this project. So I'm going to consider the case of breast cancer. I have here a 60-year-old patient, Nancy, which was diagnosed with breast cancer. Here are the various covariates or features associated with this patient. And I would like now to use this information to make predictions of mortality in the short run, in the long run. I may want to make recommendations of treatments. And the current way we are doing it today is by using methods, state-of-the-art methods such as predict, which have been already very well adopted, and they are actually recommended by UK NICE guidelines, as well as by the American Joint Committee on Cancer. Yet, when we started these projects, we wanted to understand, can machine learning do better than these methods? And the answer, we embarked in attacking this problem by using automated machine learning methods, especially a method that we have developed a couple of years ago called autoprognosis, which is a method that we have developed first for doing predictions in cystic fibrosis. But since then, we have taken it to a variety of other diseases, from cardiovascular disease to asthma, from breast cancer to many, many other diseases. This is a very powerful tool which, at the press of a button, generates a prediction score. And to our surprise, this automated machine learning method was really a lot better than predict. It was a lot better for both the general population as well as for young and old. But this left us with an important puzzle. What has been learned here? Why is this machine learning method able to do better? What is the unique source that it learns? Can I tell the researcher something that they didn't know about the disease? Can I give trust to a clinician having this machine learning method that this tool is indeed a powerful tool, and we issue predictions for the patient in front of them with confidence? Can the patient understand these predictions? So this brought me to wondering whether really machine learning can be ultimately turned into a tool for actionable intelligence. We would like to have transparency. The patients, clinicians, researchers should be able to comprehend such black boxes. Also, we would like to understand the risk that it produces, how this risk was estimated. We also may want to avoid implicit bias. We want to make sure that the model doesn't learn something we wouldn't want it to learn. Importantly, we want to understand whether machine learning is capable to learn new interactions that have not been uncovered before, thereby becoming a tool for discovery for clinical researchers. And also, ultimately, we wanted to know when can this black box model ultimately make a prediction with confidence and when it cannot. So can, for Nancy, the prediction be trusted or not? So we wanted to know what we do not know. This is a challenging problem. Interpretability has been discussed quite a lot in the area of imaging. And in imaging, this is a much simpler problem. The reason it's a much simpler problem is because the predictions are easy to interpret for us humans. If I show a pathologist that the reason breast cancer was predicted for this particular woman, and I show exactly where the convolutional neural network is looking at, that pathologist will be able to verify that, or radiologist. Also, if I predict cats and dogs, then if I say I predict that this is a cat and this is why, it's very easy for us humans to verify such answers. If you wonder where this is coming from, and you may think that this is the recent paper of Google in the area of AI for mammography, you are wrong. It is actually a paper that was written more than 2 years ago by our own lab, where we are doing this type of predictions. But what's important here is to realize that if we are to take these black box models and understand what they have learned in the case of Nancy, why a particular prediction was made, it is a lot more complicated because even we, the humans, may not understand completely the physiology that may have led to this prediction. So this is by itself a challenging problem. So today's agenda is to really try to understand what is the status quo, what is the state of the art in machine learning interpretability, and I'm going to describe different ways to think about interpretability, trustworthiness, we are going to try to issue for each prediction also confidence associated with this prediction, such that we know whether a clinician can trust this particular recommendation, and also explainability. And what I mean by explainability is really tailoring interpretability to different users. It is clear that a clinician may want to understand this black box such that they can issue a recommendation to the patient. A researcher may be interested in what the machine learning has learned and whether this provides data-driven hypothesis that they can take to the lab and verify. And the patient themselves may be interested in understanding whether this black box may guide them as to what can they do to lower their own risk of, for instance, mortality. Are there any actionable things that they can do? So different users coming and interrogating this black box model with different views. Let me start, before I talk any further, by saying this is not aimed at replacing doctors, replacing researchers. Quite the opposite. This is enabling clinicians and medical researchers with tools that are interpretable, actionable, transparent. So the focus is providing state-of-the-art technology to inform the decision makers and understand what machine learning can offer. Let me start with interpretability. If you look in the literature on interpretability, you will see a large variety of papers, and most of them take one of the following approaches. Some are saying, I'm going to provide interpretations for this particular risk by telling which features have been important for this population. So it's global feature importance. So for instance, for cardiovascular risk, it may be that the following risk factors are important for this prediction. But if we go one step further, increasingly, we realize that what made a particular prediction for one individual may be due to a totally different set of factors than for another individual. So we are moving increasingly from population-wise feature importance to individualized feature importance. And I'll talk a little bit about that. Yet other researchers are trying to provide interpretability by looking at how features interact, either in pairs or as groups. Some others may look at model nonlinearity. At the minimum, the desiderata of models that are providing interpretations should be that they should be model independent, meaning that they should be general rather than tailored to a specific black box model. So for instance, I don't want to say I have random forest, and because of that I have a very specific way to interpret random forest. No, I'd like to take any black box model and, if you like, X-ray it and tell what this model has learned. And I like to do that in a general way. Also, I would like to do that post hoc. I would like to take a model that has been trained and understand what it has learned, rather than doing that while training the model, thereby possibly corrupting the model, both in terms of bias as well as in terms of accuracy. So let's start to look at this idea of individualized feature importance as a first way of doing interpretability. So I have here Mary, and she has an entire set of features that are recorded in her electronic health record. And I'm going to use a black box model to issue a prediction of mortality due to cardiovascular disease. And now the question is why? I'd like to X-ray the black box. I'd like to understand what is the black box doing? What type of features is it looking at when issuing this particular prediction for Mary? Not for the entire population. What is there specific for Mary that led to this prediction? We are doing that with a technology called InVase, which is something that we have developed in the last 2 years. And this technology is able to look at the black box and learn that it is due to these two features, age and hypertension, that this particular prediction was made for Mary. Not for the entire population, but rather for Mary. How are we doing that? We are doing that using reinforcement learning. You have heard about reinforcement learning because all of you have read about AlphaGo. And AlphaGo is learned using reinforcement learning. We are doing here something a lot more useful than playing AlphaGo. We are going to learn what are the individualized features that have led to this prediction. So reinforcement learning usually proceeds as follows. It makes some observations, and then on the basis of these observations, it selects actions, and associated with these actions, we have rewards. In this case, the observations will be the set of features available about a particular individual, Mary. The actions will be which unique features have contributed to this prediction. And the rewards are going to be the prediction loss between the black box model looking at all the features and the black box model looking at only the subset of features. So hence, we are going to learn a policy which selects the best actions. So given the observations of the individual, we learn what subset of features the black box model is looking at to issue this type of prediction. And for that, we are using a very simple reinforcement learning method called actor-critic. Now, what does this actor-critic framework do? It's taking the black box model, which may be a deep learning model, maybe XGBoost, your favorite black box, and is going to add a critic, which is going to take the features associated with the patient and act, hence, by selecting the subset of features which are believed to be important for this individual. Then the critic takes these features and issues a prediction. It is the difference between the prediction made by this network that only looks as a subset of features and the black box model looking at all the features that is going to be the error that the actor is going to consider and use to decide in the future how to select actions. So it will learn over time through this feedback. Again, two uninterpretable slides, depending on your taste for machine learning, but hopefully they'll be sufficiently fast. So what are we really doing? We are selecting a function S, which is going to select the features for an instance, a patient in this case, X. And we are going to do that while minimizing equality constraints between the conditional distribution of the label, the prediction, given only the number of selected features, being equal to the label given all the features. We can turn this into an unconstrained optimization problem, and then you would say we are done. Well, no. It is actually a quite complicated and challenging problem. The reason it's a complicated problem is because of two reasons. If you have many features to look at, the patient has lots of information, then this becomes very complex. It's really going to be exponentially increasing in the dimensions, the number of features. But the second reason why this is tricky is because this is not an optimization problem. It's a learning and optimization problem. We do not know these densities. We need to learn them. If you are interested in the details of this, you can look at our paper. But what can we do with this? There are a variety of methods in the recent years trying to do something similar. They are looking at individualized feature importance. Some of them are model independent, which again, I think it's very important to ensure the accuracy and the bias. But there is one important thing that our method does that makes it, in my opinion, superior, in addition to the performance gains. With our method, we not only learn which features are important for the individual, but we also learn the number and the features. So it may be that for Mary, there are 2 features, while for John, there are 5. We do not pre-specify that, while the existing methods so far are pre-specifying that. So we learn not to over-explain. So, fine, are we done? Did we understand machine learning by just looking at individualized feature importance? Well, already some people will say that this is not enough because we don't know anything about the model nonlinearity. We don't know anything about how features interact. And some methods exist that are able to do that. So what we ideally would like is to have all different types of explanations, inclusively feature importance, instance-wise feature importance, understand the model nonlinearities, understanding the statistical interactions between features. But this is still not enough. Because if, like us, you are trying to develop a risk score that is hopefully going to be used in practice and change people's lives, then there are associations and guideline agencies such as the American Joint Committee on Cancer, which mandates a transparent risk equation to be associated with this risk prediction. So we cannot just give a set of features and say this is why this is interpretable. So we need something more. So this is important also because depending on the type of explanations you may want, you really want to have a transparent equation that you can use to understand what has been learned. So the question is, can we have it all? Can we make these black boxes truly interpretable? And I'm going to answer this in the affirmative. The answer is yes. With the technology which we have developed just around a year ago and has been recently published in the best machine learning conference, NeurIPS, we have developed a symbolic metamodeling approach to do that. So we take black box models, such as deep learning models or any other black box, and we are going to develop metamodels, which are models of models, that are taking these black box models and turning them into white box functions that are represented by transparent equations. So the input will be an already trained black box model, and the output will be equations like this that are going to be transparent. What is important to note here is that I don't even need to know what is this function f. I don't need to know whether it's a deep learning model, whether it's XGBoost. This can stay proprietary. So f can stay proprietary, but what I need to do is I need to be able to give it samples, instances, patients, and observe predictions. So I need to be able to query it. This is all I need. So I'm going to start with black box models, and I'm going to try to find white box models in different model spaces, and I'm going to let the chooser decide what is interpretable for them. For some, polynomials will be what they consider to be interpretable. For some others, maybe algebraic expressions where I have polynomials and roots. For some others, maybe closed form solutions, closed form expressions, in the form of, for instance, exponential functions, or maybe for physicists, Bessel functions may be more interpretable than anything else. So it is the user that will decide the space of functions that it considers to be interpretable. How are we going to achieve that? We are going to achieve that with a fantastically powerful theorem that has solved a variety of problems in a variety of fields. It's a theorem I truly love. It's also solving the 13th problem posed by Hilbert. And that is the Kolmogorov-Arnold theorem, which says that any function of many variables, a multivariate function, can be written simply as a composition of univariate functions, functions of one variable. So one can take these complex functions of multiple variables and decompose them using nice parametrizable functions of one variable. The challenge is, of course, that we don't know this black box model F. We do not know the white box model J. And we also do not know how these different nice parametrizable functions look like. We are going to try to find such functions that are going to be close to the black box model. So we are going to find parameters that are going to minimize the prediction loss between the black box model and this white box model. What type of simple, basic parametrizable functions we will use? We are going to use Meyer-G functions. For the sake of this talk, you don't need to know what they are. You can see them here. But what is important to know is that they are a very general class of functions, which for given parameters reduces to polynomials, to exponentials. So it's very flexible. So you can search within a space of solutions and identify a function in that class. How do we do that? For that, I'm going to use an analogy, a metaphor from neural networks. Most of you are by now kind of very familiar, no matter your background, with neural networks. I'm going to use that as an analogy to explain the idea. If we have deep learning methods, neural networks, we usually optimize the weights of such neural networks by learning gradients, by doing gradient descent. In a similar way, the metamodel is going to learn these parameters theta that are going to be bringing closely the black box model and the white box model using the same type of technology, gradient descent. So we are able to do that and hence search super fast in the set of possibilities because the Meyer-G functions are differentiable. So similarly to the easiness with which we train neural networks, we now can train metamodels. Okay, now we have a tool to do that. Let's go back to our original problem and try to understand what this autoprognosis learned. So we are going to understand this metamodel. And what I'm going to put here is an equation which is not quite correct. I'm just going to put here a simplified version of the equation we discovered. But we discover an equation that depends on the features that are given to us. What is important is that I can now take this equation and I can issue predictions with it. I can throw away autoprognosis, the black box model, forever. I don't need it anymore. I'm going to use the metamodel, the white box model, which has a transparent risk equation, to issue predictions. I'm going to lose some in performance. Why? Because the metamodel was actually more complicated than I'm showing to you here. It was not very parsimonious. It was quite complicated. But if I throw away I approximate it, I'm achieving something that is just slightly worse, but still a lot better than the state-of-the-art score used today. Hence, you may wonder at this stage, why do I even need a black box model? I need a black box model because this is what I'm trying to interpret, but also I need a black box model to guide me to find this metamodel. I would not have found this metamodel if it was not for this black box model. But now that I have it, I have an equation which I can give and I can start to interrogate. In reality, what we learn is actually something really very interesting. We learn different types of equations for different grades of the tumor and ER positive and ER negative status. And a very interesting analysis has been happening actually by us by using this black box model and trying to understand it through the metamodel. But as I mentioned, there is a little bit of a challenge. We love regressions, we love linear models because they are transparent as well as parsimonious. These metamodels are transparent. I can produce for you an equation, but some of them may not be parsimonious. So the question becomes, can I find simpler equivalent expressions? And the answer is yes, I can do that very easily. Now, because I have an equation, I can start to do lots of interesting things. I can simplify it, and I can see what's the impact on it. I can linearize it. I say, I'm insisting on linear models. Well, if you insist on linear models, I can tell you how much you lose by insisting on that. I can do subgroup analysis, but also I can do some miraculous things with respect to individualized feature importance. I'll talk about that. So already you have seen our method in VASE, which was able to say that for a particular patient, I have this cardiovascular risk, and these were the features that were important. Now I can do something much more interesting. I have a black box model that I'm not even showing to you, which led to this white box model, shown in here, this equation. And now I'm interested for a particular individual. What is the impact of one feature? For instance, age. on the prediction given the other features. Why is this so interesting? Because now I'm no longer saying age, BMI, and diabetes are important. I'm able to tell you, given the age of a person, or as the age of a person changes, how the other variables become more or less important. So I'm getting a relationship of how these features may change their importance with respect to other features. This was not possible before. But it's possible now because we have such a transparent risk equation. I can also say this is too complicated for me. I have here something I really don't want, a fraction that I don't want to deal with. I can simplify that. I can throw that away, and I can see what's the impact on that, either on the individual or the subgroup. And this is what I'm doing in here. For instance, I want for women to identify what's a simpler equation than the equation which was found for the entire population, and I can do that. Now that I have this tool, I would like now to build explanations. And we already decided that different explanations are needed for different users. So I'm going to use this meta model in two different ways. In the forward way, I'm going to put as input the features of the patient, and I'm going to output the risk, such that, for instance, a clinician can understand why a prediction was made. A researcher may want to understand how the variables interact. But also, I would like to use it in the backwards way. I would like to tell a patient or a policymaker, I would like a decrease in risk of 5% or 10%. What features are going to lead to this reduction in risk? This could be useful for dosage recommendation or policy design. Let me show to you how. So first, I'm going to start with the researcher. The researcher, I think, will be fascinated by seeing that this prediction is better and try to see, is there something there I really can understand? So, for instance, in the case of this breast cancer example, two things that we have learned that we are now working with researchers to try to understand whether they are indeed reflective of the reality of the human body. The first is that while it is well known that there is a difference in patients' prognosis and reaction to medication on the basis of ER status, what we discover is that it is the grade of the tumor that's even more important when doing subgroup analysis and understanding risk. So you want to first stratify with respect to grade and then to ER positive and negative. And the equations that are going to be resulting are going to be really quite different. Another thing, it is well known and actually used in methods that are used today, such as predict, that risk grows quadratically with age. But when we discover that this is also true, that risk grows quadratically with the number or affected lymph nodes. These are hypotheses that are generated by the machine learning model that, of course, will need to be taken to the lab and understood. We have different machine learning models. And the reality is we can try to understand using these metamodels, this white box model, what have they learned? And we can see whether these different white box models agree with each other. If they do agree and they do common discoveries, then maybe we have more confidence to go to the researcher and say, look for these discoveries. But maybe the most important reason to build this is to help clinicians make better decisions for their patients. And now that we are able to do that and X-ray these black box models and use transparent risk equations, we are able to tell the clinician that even though we have two patients with almost the same features, the reason the risk predicted was very different, and hence the treatment recommended was very different, is because the number of affected lymph nodes led the risk to grow quadratically, even though all the other features were very similar. We can also use that for policy making. So, for instance, the age at which women are given mammograms is often mandated. In different countries, it's at different ages. Let's assume it's 50 years of age. And we know that this is not a good approach. There are women which may have family history or may have the BRCA mutation that clearly need to be screened much faster. Some other women, maybe it's okay to screen them at 50. Some others, maybe we can even delay. And maybe some other women have a very low risk and don't even need to be screened, thereby using the available resources a lot better. This is very easily done now that we have a white box model. We can just invert it and tell what will be the age at which I should be screening given the features that I have about the patient and the risk at which I'd like to screen. Something that is not easily done otherwise. Also, I may want to tell the patient what can they do to modify their risk. For instance, they may be able to lose some weight, do some exercise, and maybe that will lead to a certain reduction in risk. Note, though, this is about correlations. This will be a hypothesis that can be taken to understand whether indeed BMI does affect risk. And of course, associated with it is the whole agenda on causality that goes beyond correlations. And actually, our lab does a lot of work on causality, but that's a subject of a different talk. Instead, where I'd like to take you next is using machine learning to build better collaborative systems for clinicians. Machine learning-enabled healthcare systems. The way we are proposing to do that is by viewing them as a recommender system. A lot has been written in the media, and rightly so, about how unhelpful the current electronic health records are for clinicians. And EPIC has created a horrible mess. And clinicians are inundated with a lot of information. They need to fit in a lot of information themselves. And this is of a one-size-fits-all. So what are we trying to do here is to use recommender systems. And all of you are familiar with recommender systems because when you go to Netflix, it will recommend you a good movie. When you go to Amazon, it will recommend to you the right pair of shoes. Here, though, recommender systems are a lot more complicated. They are not just recommending you a movie, because the clinician may see different patients in different stages of the disease, may see the same patient over time, and also may learn over time how to better interact with the system. So the way we are actually viewing this is as a new class of recommender system for which we build totally new tools. And this is part of a long agenda where we have been involved for many, many years on personalized education. But the focus here is really rebuilding this ecosystem such that when the clinician sees Mary as opposed to Nancy, or when the clinician is this type of cardiologist rather than an interventionist cardiologist, will see different views and they'll be accessing different types of information and they can interrogate these machine learning methods in different ways. I'm going to use not the real, and we have done that in a set of papers actually with a master student and build such systems. But here I'm not going to show you the real system, I'm just going to use a stylized example. So we have Betty, who is 86-year-old and has a quite high chance of dying within 1 year. And we can create different types of explanations for the clinician as to why this particular black box has predicted this. We can show individualized feature importance. We can show a risk equation. We can also do a decision tree. And we can say it is based on these features that this black box model has learned this particular risk. And as a matter of fact, we have in this clinic 79 patients that are in this category. Hence, the clinician can understand that and can look also at similar patients as Betty that are in this cluster. He can even go one step further and say, are there patients like Betty but which did well for a long time? And what have they done, for instance, in this case, exercise, to be able to survive? We have done that and actually experimented with this machine learning method recommender system with 19 cardiologists with different types of subspecialties in 4 different countries, seeing very different types of patients. We had young clinicians and older clinicians, some of them very big geeks, knowing very much about machine learning, some for which they knew nothing about. The reality of this exercise, which is summarized in our paper, showed two important things. First, each clinician wanted something different. It brought us completely to the belief that we really need to have personalization. The clinicians need to see different things, need to interrogate the available knowledge in different ways depending on their sensibility and their patients. And this is possible using machine learning. But there's one more thing. There is one other commonality. While different clinicians want a different form of interpretations, they all agree on one thing. They wanted to have not only interpretations, but also to understand how confident the black box was in issuing this prediction. Can they really trust the black box model? So that brought us into a new agenda on trying to understand how much trust we can have in these predictions, because we know that machine learning is very accurate, but often we cannot quantify how certain the machine learning model is in issuing these predictions. At times we may be very confident, at times not. And we really need to know what we do know, whether for Nancy we are very sure for the prediction, but maybe for Mary we are not. So what we need to do is to quantify uncertainty. And we would like to do that by issuing coverage. So we would like to have uncertainty intervals that contain the true outcome. The true outcome is in these red dots. So we would like that the confidence intervals contain these red dots. So here we have coverage, while here we do not. We also want discrimination. We want that as we have more patients, for instance, middle-aged patients, the confidence intervals get smaller, get tighter. And when we have very few patients, for instance, young or old, we would like them to grow wider because we are not very confident. So what we would like to have is coverage and discrimination. We would like to be in this situation. Now, state of the art in machine learning is not able to give us that. We have a variety of methods, but these methods don't work very well in practice. And even more importantly, they do not provide post hoc analysis. I cannot take a black box model and then determine how confident I am. And also, I cannot provide coverage guarantees. So we have embarked again in a quite long research agenda that is quite technical, so I will not bother you with that. But we are able now in a suite of methods to provide really frequentist coverage that is post hoc, and we have guarantees for it. And this is important because we are able to provide guarantees and not interfere with the model. So we can now go back to Nancy and decide how we should treat Nancy. When I give this talk together with Jem Rashbas in middle of last year, we were showing you this type of graphs where we were saying for particular person, Nancy, we predict that actually using chemotherapy leads to a better outcome than for the general population, for which is recommended chemotherapy and radiotherapy. So we were saying this person is different, and we are able to predict that for them something different is important. Now, we are able not only to interpret this prediction, because we have these new tools, but also to provide confidence estimates associated with it. So we are able to answer causal inference questions. What if Nancy was treated this way? What if she was treated that way? And be able to issue predictions and confidence associated with it. Our lab is doing a lot of work on causal inference because we are very interested in understanding outcomes of treatments. And that's, of course, a much more complicated question than just predictions. But we are able to do that with confidence. So we can issue trustworthy recommendations. And maybe for some patients, we are able to issue them with confidence. And for some others, we say, we have no idea. Don't trust the model. Use your own judgment. You cannot be confident in what we are telling you. So with these types of tools, we are now able to equip clinicians, patients, and researchers with interpretable tools that are trustworthy and hence actionable. And our entire research group, my lab, which is called MLA, Machine Learning and Artificial Intelligence for Medicine, is building cutting-edge machine learning methods to help with the hard problem in medicine and healthcare. And we are doing that by looking and combining a variety of principles that transcend just one field. It is not just machine learning. We made these advances because we married ideas from machine learning with ideas from statistics, powerful ideas from statistics, machine learning combined with applied mathematics, as well as operations research, and last but not least, to be able to run such systems at scale, distributed computing. And this is, of course, not possible without numerous clinical and medical collaborators that are guiding us and inspiring us. I'd like to thank very much Professor Wilson for inspiring me to look at this research agenda and helping and pioneering this research. My former student, now postdoc, Ahmed Allah. My collaborators, William Zaim and Jem Rashbas. Sean O'Neill from the Alan Turing Institute, who helped me make this talk slightly more interpretable, hopefully. And the many brilliant students that this work is based on. And if you are interested to learn more about our research, please visit our website. Thank you.
Well, I'll start with a very quick thank you. I mean, that was a brilliant exposition of something complicated. Now, I would like Mihaela to stay there. And really, I've got a couple of questions I'd certainly like to ask myself, and I'd like to make a number of comments. But let me just open it up straight away and invite questions, comments, number of hands, which is great. Can you just say who you are and where you're from, just so we can position you where you're coming from on your question? I'll start there in the middle.
Adam Wise at City University. I wanted to ask about the methodology where you're going from your input data.
I'm sorry, I think you're supposed to have a microphone. Oh. Yeah, there we go. Sorry, we'll do better with that next time.
Sorry, can you hear me?
Yes.
Good. Okay, so the methodology kind of the first part was kind of you're starting with your input data. You then have your AI system, and then you turn that into a white box, kind of your equations. And the question is the AI system ultimately kind of logically redundant? Because you could just take the input data and generate the white box equations. The only difference I can think of is generating synthetic data for the white box, but that synthetic data must have some questionability because it's going beyond your input data.
So thank you very much for the question. So multiple things there. So first, the black box model is needed. I'm using this black box model that I need to understand. So I'm building the white box model to interpret this black box model. It is this black box model that is guiding me to find this white box model. This is what I'm finding through this gradient descent algorithm. If I don't have the black box model, I cannot find it in the wild, or at least we do not know how to do it today. So two answers there. First, don't forget, we are having black box model that we would like to understand. This is the goal. The goal is not to throw away the black box model, but to understand it. Answer number two, I even need the black box model to guide me to find the white box model, after which I can throw it away. The issue of synthetic data is a completely different question. We are doing a lot of work on synthetic data. And you can find quite a lot of work even here, synthetic data. This is more about generating synthetic data to give to researchers to be able to train their own machine learning models. One of the biggest challenges we were very fortunate to work with Public Health England and have access to data that was wonderful and that enabled us to do the research I presented to you. But many of my colleagues are not as fortunate to have access to such wonderful data. So hence, synthetic data and privacy-preserving synthetic data is important, not to build the models necessarily, but rather to liberalize these ideas and allow all machine learners to have access to high-quality data that is private to train their models.
Okay, but what I'm not understanding is, given you end up with white box equations, what is the black box really adding? because you have your input data, you end up with something which isn't the black box. What is logically the black box adding that you couldn't, in principle at least, have achieved just from the input data?
As I mentioned already, we have the black box, and we would like to understand what the black box has learned. So first, we are X-raying it. Number two, as I mentioned, you will need to do, you are learning the white box model not on the basis of the raw data, but on the basis of the black box model. So it is the black box model that is guiding the construction of the white box model. So you cannot do one.
I mean, that question was in my head as well. I mean, my understanding of it is you need what is, in a sense, the data from the black box model in terms of outputs in order to get to the equations, and you can't get directly to the equations. But once you've got the equations, you can use them. Although there was one throwaway line, Mihaela, if I heard you correctly, which is the predictions from the equations are almost as good as the predictions from the black box, but not quite as good. Yeah. Right, move on in the middle there. Sorry, there's a microphone on its way there.
So on a similar topic of the metamodel.
Can you say who you are?
Oh, I'm sorry, I'm Paolo Missiera, Newcastle University. So when you're learning metamodel, are you assuming that you have access to the original training set data that was used to train the black box model? And if so, why do you need it? If not, what's the size of a training set to basically generate a valuable metamodel if you don't have access to it? So basically, how many new examples do you need to query the black box model to generate your metamodel? If that makes sense?
Yeah, that does make sense. So right now, I can use a subset of the training set, but I don't need that. I can create my own examples and use those, issue predictions on the basis of the black box model, and use this new data set. So thank you. This is a very important question that I realize only now. I should have explained, and it was not transparent. So yes, so I don't need the original training set that the black box model has used. I can query it myself, and I can determine a data set of inputs and outputs that I now use. But this brings me up to another question. What happens if I train the model in the UK, and I'm now going to use it in the United States? We have done a lot of work in this area, where we are transferring what we have learned in one location to another, and learn when can we have confidence in this transfer and when we don't. So if you are interested about that, you can look at some of our papers, or you can email me. So this is a very important, related but different research agenda. When can I take models from one environment and with confidence or not translate it to another? But that's something a little bit different that is true for black box models as well.
Thank you.
Right, I'm going to go down to that side. No, can you take that microphone the other way, please? And then we'll have it, pass it down that row to the, keep going. And then you're next after this. Right, you go now.
Chris Wigley, Genomics England. The examples that you gave here had a finite and reasonably small number of features that we were talking about. Age, BMI, blood pressure.
What happens if there is genomics?
I'm going to get to genomics in 1 second, but I think even before you get to like 6 billion variables of like the letters, right? Have you looked at scenarios where you fed into these methods models that have been derived from hundreds, thousands of features, and maybe that you derive using AutoML kind of methods to, that it's some combination of, okay, this person was seen at this hospital, and they happen to be this age, and they happen to be this ethnicity, and so on. And this question, part A of the question. Okay. Part B of the question is, can you use expert input to narrow the solution space? So can you, in the same way that you're proxying the black model with the proxy of the white box model, can you proxy some of the feature selection by using expert input from humans to collaborate with the AI?
Thank you. Very, very, very good question. So, okay, so multiple questions there. So first, let me just take a little bit aside this issue of AutoML. As you see here, we are doing a lot of work on AutoML. But AutoML is not necessarily, it's just simplifying, it's trying to put the machine learners out of the job. So people say, oh, Mihaela, you're trying to put the doctors out of the job. No, I'm trying to put the lazy machine learners out of a job by creating automated machine learning methods that will do the job. Automated machine learning methods are in development and more powerful. but I don't think that they necessarily have as a goal dealing with very high dimensionality. The focus is mainly in taking a problem and learning in an automated way what hyperparameters, what algorithms to choose, etc., etc. But going back, so forgetting about AutoML and thinking about large number of features, that's when things get indeed tricky. So if I have a lot of variables, then I need to do exactly what you say. Either I may need an expert to tell me, look at this bunch of features, or I am going to use a machine learning method to do, for instance, discovery, which variables are indeed important for this label. And we are doing a lot of work again in that area on trying to identify variable importance given false discovery rate guarantees in high-dimensional settings such as genomics. So then we do the type of pre-processing either with a human being or with a machine and feed that. Can we do better than that? I don't know. That's one of the things we are working on as we speak. But you are right, this is a vulnerability. If I have thousands of variables, I will need to do such pre-processing. Otherwise, it's impossible. And also, if you have that, it becomes much less a question of just what the machine learning model has learned, but it starts to be a first question, is this pre-processing step? Which variables are truly important, and can you give me guarantees such that I, the medical researcher, can go and only test this hypothesis?
Right, I'm going to go to there first, yeah.
Thanks very much. Tom Daniels, Southampton. Mihaela, thanks very much. Great talk. As a clinician who's not a mathematician, I just wondered if we could change tack a little bit. I'd like you to make some predictions of your own, and I wonder where you see this work going in the next 5 years and the impact on clinicians on the front line.
Thank you for that question. So what I hope is that, I need to say that Tom is a collaborator, and I have the pleasure to work with him on cystic fibrosis and a couple of other projects. So where I would hope that we can take this project is really to build machine learning-enabled decision support systems that first can be tested at length together with clinicians such as you, such that hopefully they become not only transparent but also useful. So rather than dumping another risk score on you or another prediction on you, try to understand what's useful, what's not, how to be presented. So go through a debugging stage. And then hopefully we can equip clinicians with tools to make better predictions for individuals. I think that this is extremely important, especially in cases where the disease may be complex, like cystic fibrosis of certain cancers, where the prediction is not only about now, it's also about integrating past information, clinical, and complex genomic information. Let's be honest, it is very complicated for a human being, even a very smart human being, to understand differences and to be able to integrate such information. So where I would hope that this technology is going is in a debugging stage. I'm hoping to be able, together with collaborators in industry, to bring some of these models to real systems that can be debugged by clinicians, and we understand what is useful, what's not, maybe go back to the drawing board, and hopefully enable clinicians to use these tools to make better predictions, whether it's of treatment, whether it's of prognosis.
Right, I'm going to organise the logistics of the microphone. Can you pass it on that row, please? And in fact, one past you, then it can come back to you. Okay, two past you. So, Janet, you go next.
Thank you, Mihaela. That was a lovely talk. I'm Janet Allen. I'm from the Cystic Fibrosis Trust. One of the issues that, is that our understanding of disease models, our understanding of pathophysiology is always changing. And your input data now may be very different from your input data in 5 years' time. Can you help us identify where the holes are in our knowledge base in that pathophysiology so that we could actually direct our research to focus on the missing factors? Does that make any sense?
Makes perfect sense. So thank you, Janet, because you are one of the most important motivators of a lot of research we are doing. This is where my hope is as a researcher, that we can build some tools that provide physiology researchers, medical researchers, unbiased tools that are not based on our beliefs, but rather based on the evidence of data. This doesn't mean that everything we find will be correct, but what I hope is that some of these tools are going to be almost like a microscope to try to identify new interactions, new features that may be important in the context of other features, and not for everybody. Maybe depending on the specific individual, some things will be important versus others. I do think that this will not be enough. I think that this is just tools we can equip researchers who want to have better tools to investigate and put their own questions. So the way I see it is not us machine learners doing that. I see us building a whole set of methods to equip clinical researchers now to look at data with new powerful tools and do their own discoveries, and then come back to us, the machine learners, and say, I will need something different because what I see here needs to be understood in a different way, or I would like to incorporate this or that.
Okay, I'm going to, I've got lots of questions. I'm going to try and do the logistics of the microphones. Well, so Janet, can you pass two in that direction? Oh, you've got it. That's the next one. And then I'm going to start. Can you pass the microphone along that row you're on now to the gentleman in the middle with his hand up? And I'm going to, and then after that one, Jesse, if you can get the microphone back and bring it to the front row. I've organised 3 questions then. Right, where you go.
Hi, thank you, Mihaela. I'm Eleanor from the University of Edinburgh. And you briefly mentioned interpretability in images at the very, very start. And I was just wondering if you see a natural extension of the in-vase method to images, where the interesting features might be something like shapes or textures or edges, which are different from the input pixel values.
If you are working in that area, I would love to work with you on that. I used to do imaging in my past life. So long ago for my PhD, I used to be doing imaging, but that's really long ago. What I think is interesting is even something a little bit different. So we could look indeed, like you say, and I think it will be very interesting to understand shapes. But where I would like to take that together with a partner would be to look at imaging and non-imaging features. Imaging and genomics information, for instance, imaging, genomics, and clinical, and understand those interactions. That's where I'd like to do it. Because if I just look at images, it seems to me, again, radiologists, pathologists are very good at looking at these images and discovering very important things. But if they need to integrate in their head that with the longitudinal pathway of the patient, with the genetic information, that may be much more complicated. And that's where I would say the frontier would be. Yeah.
Let me make a comment before we go on. I mean, there's an interesting theme developing here, which I think Janet started. And one thing you said as part of the lecture, Mihaela, which you talked about now, is how these procedures can, in effect, create new science. By leading, physiologists or whoever into it, the causal explanation of the mechanisms. My question is always the famous, what I always quote is the Mike Lynch question about a big challenge for machine learning is how do you actually incorporate prior knowledge? So if it goes the other way and there's new science, how do you feed that into a machine learning algorithm? And there may be no answer to that question, but let me put it.
You already mentioned one simple way by letting the researcher kind of narrow down the variables they are looking at, so kind of focusing the microscope towards a specific area. I think that this is a very good question that I need to think much deeper about. But right now I would say, given what the machine learning model learns, I can see first, I can test what it has been learning, and I can verify whether I can see the same type of interactions I expect. So more as a validation and an interrogation and a debugging of this method. As a pre-processing step, which is kind of another way I see it as feature dimensionality reduction and looking at that. But I'm sure there should be better ways to do that. And I think that that's something, food for thought.
Okay, I'm going going to move on. I'm in the middle of that row, I think, now, yeah.
Hi, I'm Matthew from Springer Nature. I was wondering, in the loss of accuracy from black to white box model, is there anything you can learn, like say, do some black box models have greater loss than others, and maybe what you can learn from that loss and feedback?
So again, this white box model that's resulting on the basis of this black box model may be quite long. Yeah, that's the reason this issue of parsimony may be quite long and may have many parameters and many terms. Some of these terms, because now I have an equation, I can say, are they pertinent to the entire population or only a subpopulation? That's number one. Number two, I can say there are some nonlinear terms. Whom do they affect? I can compute that because now I have an equation. So the beauty of these equations is that now I can really quantify for whom I'm losing in performance and what I'm losing due to. So I think that that's the beauty of it, which may also lead to some better understanding of what's happening.
Okay, can that microphone go diagonally 2 forward? And then front row, please. You're next, yeah. You go. Yeah. No, you go now.
Okay. Thank you for your presentation. Yeah. I'm from National Health Service, cardiovascular outcome research. We do use logistical model to predict risk score of patients. So instead of using advanced machine learning model, I think that one thing is that it's good to improve the accuracy. Another part is the transparency. If there are 2 models with 70% of accuracy and 30% of interpretation, and another model has using the machine learning model with 90% of accuracy, but only 10% of interpretation, I think probably the cardiologist or clinician might be choose the first model to use, basically.
So thank you for this question. So first, let me start by talking about Q-risk, which is often used in this country for cardiovascular disease. I talked to many clinicians and GPs, and they all say Q-risk is uninterpretable. That's number one. So what we are using today is highly uninterpretable. But what the talk today tries to give to you is to say, you no longer need to make the choice. For the first time now, because we have this way to turn black box model into white box models, you can have accuracy, high accuracy, interpretability. I can give you an equation, and the only difference as opposed to a simple white box model like a regression is that I may have some nonlinear interactions. Granted, you don't want that nonlinear interactions. You may end up with a linear model, which may be the same as a regression model or not. But even more importantly, I can also give you confidence. I can tell you when this model is going to be leading to an accurate prediction for this individual. So I'm trying to say that I think we can have the cake and eat it too, because we have models which are now explained by equations. You can decide how complex you are willing to understand that equation. You can do simple cluster analysis with it. You can do everything you want. And I'm giving you confidence associated with it.
Yeah, thank you. I have a second question, which is that we have a different model in the different domain. For example, we use the Euroscore model for the coronary artery disease, and we use the PRAISE model, which is the partial risk adjusted model for the congenital pediatric heart disease patient to predict their risks of death. So do you think that in the future, in the machine learning model can have one fit for all model can be applied to all the domain with different heart disease or not?
I'm not sure I completely understand the question, but it's clear that machine learning models learn different interactions between features and possibly different nonlinearities for different subgroups. So actually, I am offended by people who believe that in complex diseases, having one equation for everybody, whether it's linear or nonlinear, will work. The reality is that these machine learning models, one of the first things they learn is exactly this type of indirect, not explicit, but implicit clusters that have different interactions between the features, and they discover them in a data-driven way. So I think that this is something inherently happening here. Bringing this to make predictions, I think, is quite nearby. Using this to make discoveries, like Janet was asking me, I think it's the next frontier, because then you would like to start to answer questions. What has happened in the physiology of this subcluster that led to this very different set of interactions being predictive?
Right, I'm afraid I'm going to take this is the last question, okay? Where was it? So who's yeah, let's go in that direction, yeah. So I'll take, here's a microphone coming. I'm going to take you as the last question. I might allow myself to ask a question then at the end. Okay. So, anyway.
Hi, Mihaela. Fantastic lecture. I'm Tony Wood. I head up medicinal science and technology at GSK, and so I'm a researcher, right? I'm particularly interested in the opportunity in the white box method to begin to think differently about what we measure. The challenge I face, particularly thanks to gentlemen like the one on my right, is the explosion of things that we can measure. I think this idea that you can use the method, reduce to equations, and then look for collinearities and factorization of the variables in those equations to go back and say, oh, this one I know factorizes to another 3 variables. How does my model change if I go back and measure those rather than the thing that I did measure? Or this collection of measures, they all sum up to one thing that's much easier to do. I'm really intrigued by the method that we could put in place to fix that sort of problem. For example, you know, your point about genomics, I have no idea whether the stack from chromatin structure accessibility through to an image via proteomics is going to just cost me a fortune or inform me really very, very well. I'm hoping you can help me with that problem.
I love the question because we already have methods to do that. We have already thought about that and already do that. So there is a whole set of methods that I can point you to where we have tried, not in the genomics area, but in longitudinal trajectories and complex imaging and non-imaging information, where we look at the value of information given other information and how this value of information changes over time in the presence or absence of information, and in the long run as opposed to short run. We already have developed such methods. And I need to say, as in my master's degree, I used to be an information theorist. These are the first questions an information theorist will ask. What's the value of information? And is there cheaper information that may bring me there as well? And when? And for whom? This is what the talk today is also saying is for whom. Because for some people, it may be important to collect this information. And for some, it may be important to collect it now, while for some others, I can wait. We already have a suite of technologies to do that. More will need to be developed, especially if we have genetic data that's very high dimensional. But for longitudinal trajectories, for multimodal information, we already have good and robust tools to do just that. So thank you for the question. We should show to you these methods.
Okay, I'm going to wind up now. I want to make a couple of comments. First thing to say that I would like to say is, what this reveals, it's coming out in these kind of questions now, is the scale of development work as well as research work that has to be done to actually, so I hope the budget today will produce some research money that will help that, and GSK and other big companies will contribute as well. But, there's a huge program to be driven there. But there's a corollary of that, which is actually quite important, which is something that struck me when I first started working with Mihaela, which Mihaela is well aware of. It's a generic problem. So one of the other projects we're working on within Turing using this kind of technology is instead of having a flow of patients, you have a flow of offenders. and prisoners, you're actually doing rehabilitation plans instead of treatment plans. And, that's simply not even been started. I mean, we're in a field where a tremendous amount of work has been done, but there are lots of other fields where, the same concepts can be applied. So, really look forward to developing that as well. And, those kind of things are at the top of the Turing agenda. And I'm going to resist the temptation to ask my questions because there's actually a wine reception waiting for us outside. But before I release you to a glass of wine, I want to thank Jesse and colleagues for actually organising this. I want to thank the staff of the RSM for taking care of us, and indeed for the RSM to organise it. We've had a number of Turing lectures here now, and it's a fantastic site for us, and I'm sure we will be back. And finally, of course, I want to thank Mihaela. I mean, it was a brilliant, fantastic lecture, and I can see that from the reactions of all of you here. So I'll say thank all of you for being here and being such a terrific audience. But at the end of the day, let's thank Mihaela for a terrific evening.